Welcome to springlib.
All right, so we have some sort of material that's bubbling here in this sort of area. And you have droplets of this material that end up shooting outward. There's one droplet right here, and there's one droplet right here. And the interesting thing is they both launched outward at the same initial angle, just opposite directions. And they also are moving at the same velocity. And there's a distance between these two objects, which is actually, as you'd imagine, is going to increase over time. This distance d here. All right. So put this to the side here. We'll get right to work. What I'm going to do is I'm going to just treat one projectile at a time. I have projectile 1 over here, and projectile 2 over here. So starting with 1, I'm just going to write the coordinate of this projectile over time. And we're going to use a larger bracket here to describe that, and it's going to be equal to the velocity initial times cosine of the theta, because we're looking at this position down here. So we're going to use cosine theta times t. And for the y coordinate, we're going to use then the velocity times time, but this time it's velocity initial times sine theta multiplied by t. And since it's fighting gravity, we'll do minus, this time minus the 1/2 gt squared. Usually this equation has a plus 1/2 at squared, but we're putting a minus g in for the a, and we pull the negative out front. Squared. Cool. So that's a coordinate to describe the position of this first projectile, and we're going to do the same for the projectile 2. We're going to call it x2, comma y2, and go ahead and use the same technique now. Make sure you're consistent, though. Of course, I guess I probably, going back, I can be a little more clear about this, and you'll see in a second why. I want to call this one projectile 2. And this one's projectile 1. Of course, that barely changes anything, but just to be clear. So this is projectile 2. Here's my axis system. This is positive y. This is positive x. So then everything matches up with this one. But since this is the minus x direction, my velocity here or my position here for my x has to be negative. So we're going to put a minus velocity initial cosine theta times t, comma, and then for the y coordinate, we'll use, this one's going to be positive because it's positive just like the other projectile, and the initial sine theta times t minus 1/2 gt squared. And close down that bracket. So these are just very large, basically a coordinate point that changes with time as you move forward. Now, what we want to do, though, is we want to find the distance between the droplets as a function of time. So as these two droplets move apart, you got to figure out a function of time for that. So we know that the distance formula, which is just simply from algebra, we can use that perfectly here, since we have positions for both the y and the x for both droplets. So we'll use x1 or x2 minus x1 squared. And this is really just an extension of the Pythagorean theorem. And then we'll have a y2 minus y1 squared. All right. And the distance then, if you plug in all the information that we have here, starting with x2, you're going to have minus vi cosine theta times t minus x1, which is vi cosine theta times t. You can put those together into here and squared, and then plus the y2 minus y1. So the vi sine theta t minus 1/2 gt squared. And then we have minus, since we have two parts for y1, I'm going to put parentheses here, vi sine theta 2, or theta times t rather, minus the 1/2 gt squared. We'll close down this bracket. There's also that second bracket there we've got to close down. And this is a huge root here. Cool. It's not easy to extend that all the way across the page. Whoa, there we go. Cool. Awesome. All right, so a few easy things here that are convenient for us. This right here and this right here, they're the same thing and they're subtracted, so these essentially go away completely, which is really nice and convenient for us. And here we have a minus something minus the same thing, so it's going to be, let's just put it on here, d equals, we'll have our 2. No, actually, put the minus 2 vi cosine theta t. And that's squared, which is very fortunate for us, so it can actually clear that negative up front, otherwise we'd be in trouble with the root being here. Then we'll get 4 vi squared cosine theta squared. And then once you go ahead and you do this root here, you get d equals 2 times velocity initial times cosine theta times t. And that gives us our function of the distance between those two droplets as a function of time.